Welcome back, everyone. It's good to see so many familiar faces. And good morning. I'm glad to see everyone is bright-eyed and bushy-tailed. This course is called Advanced Quantum Field Theory, the Theory of Elementary Interactions. It's going to build directly on the previous quantum field theory course. That means that everything that happened in the previous course, I'm going to assume you know. If you don't remember anything from the previous quantum field theory course, please do check out my videos on YouTube. There, everything is available. This course is going to be aimed at explaining the standard model. So the big goal is to explain the standard model of particle physics. Now, that task we will not succeed at in this course. We don't have enough time. I would love to explain all the derivation, all the history behind, all the properties of this standard model, but we're never ever going to achieve that in the 20 or so lectures that we have allotted to us. Instead, I'm going to explain the building blocks of the standard model. The goal is not to explain every term in the Lagrangian of the standard model. That would just take too long. But instead to explain the main ideas that the standard model interactions are built on. So for that, we're going to need to talk about the quantum field theory of bosons, which we've already met, the quantum field theory of fermions, which we've already met, the quantum field theory of gauge bosons, or Yang-Mills theory. That's something we haven't yet met. That's something we're going to focus on a lot in this course. We're also going to talk about certain mechanisms known as symmetry breaking mechanisms. And with those main ideas, you'll be able to at least look at the Lagrangian for the standard model and point at each term and understand where it comes from. What's the, what do these interaction terms describe or pertain to? So this is that's the actual objective of this course. The Lagrangian itself is so long that I won't ever write it out in this course. You can, I invite you to look it up on Wikipedia. All right, we're going to have two textbooks that we're going to follow. They're familiar to you already. So firstly, we of course will have Peskin and Schroeder, although the material in this course is not really taken from this textbook. I use it as a guide to the subject matter. And another one that I really like a lot at this stage is a book by Tony Z called Quantum Field Theory in a Nutshell. So this is a fantastic book. It's not at any level of mathematical rigor. It's a very intuitionist, physicist's description of quantum field theory. But it's one of the few books where you get at the ideas behind all the stuff we're doing in quantum field theory. Usually you get a bit lost when you look at a quantum field theory textbook and sort of, what's the big picture? Why are we doing this? What's the big idea? So, but this book is a very rare counterexample to that, and you get to see lots of parts of quantum field theory and have it explained to you in a very relaxed manner. However, it's a very demanding book. It's not a good first textbook, because many of the derivations are simply not included in there. You have to go out and, if you want the details, you have to work them out yourself or find them in another textbook. So somehow these two books together are the inspiration for this course. There's a lot of stuff in here which is in no textbook. So I cannot give you a book. You just have to watch the videos or take down notes or both. Because I'll be telling you stuff that comes from current research, and I'll be telling you stuff that is collected from various research papers here, there, and everywhere. So this course is very much not following a textbook, but that's the backbone will, in some sense, be guided by these two books. Okay. I guess that's not the most interesting stuff, though, of course. We'll have to discuss the Prüfungsleistung. Okay, like last semester, this will be an oral exam, and the Studienleistung, exactly like last semester, is greater than 40% on assignments. There will be, I believe, 6 homework assignments. Once you've achieved a mark of greater than 40% on these assignments, then you'll receive the Studienleistung. And if you want the Prüfungsleistung, then you need to register for an oral exam. That's quite easy. Just send me an email towards the end of the semester and we can organize that. Okay, so now let's talk a little bit about the actual topics that we're going to cover. So topic 1 that we're going to be concerned with for the next couple of weeks will be path integrals. You've probably met them in some form before, but we're going to start from the beginning. It's a piece of elementary non-relativistic quantum mechanics, discuss path integrals, and then we're going to immediately start applying them to quantum field theory to give us what's known as path integral quantization. Now, you know my position on quantization. What we're really going to be using path integrals for is as a guess to build quantum field theories that have the right classical limit. So we have to discuss path integrals at the beginning of the course. And actually, largely everything I say on the non-relativistic side will be rigorizable. So you may have heard various things about path integrals. Well, yeah. So then we're going to, we're going to take a quick review of perturbation theory, but this time from path integrals. We're going to see a lot of familiar words. Wick's theorem, Feynman rules, blah, blah, blah. And the beauty of path integrals, and I hope to convince you after a couple of weeks, is that you could spend an entire course on canonical quantization of quantum fields and arrive at the Wick's theorem, Feynman rules, etc., etc. But when you express things in terms of path integrals, they become so incredibly simple. So Wick's theorem, which I know you've all memorized, becomes something absolutely, it's essentially a triviality when you learn about path integrals. So the proof was relatively tedious and intricate, the proof I gave last semester. But the one when you use path integrals is just a straightforward consequence of my favorite things, which are Gaussian integrals. So I forgot to specify that we'll essentially only be looking at Gaussian path integrals at the beginning of this course. So the beauty of path integrals is that they reduce many things that were tedious or difficult in the canonical formalism to something that's a very simple consequence of known facts about Gaussian integrals. It's amazing, it's very beautiful. And then we're going to talk about renormalization. I already gave you a very superficial overview of what we mean by renormalization in quantum field theory. Here we'll spend a little bit more time on that, go into these ideas more deeply, and discuss effective quantum field theory a bit more comprehensively. So the one point I want to maintain throughout this course that I started making in the previous course is that there are no infinities in quantum field theory, contrary to what you've been told. Every quantity that you calculate in quantum field theory, every prediction for a physically observable quantity does not have an infinity in it. These infinities have to do with something else, and this idea of effective quantum field theory immediately eliminates all these affinities. It leaves open some other philosophical problems, however, which we can't solve. All right, then we get on to the real topic. Well, in some sense, this is the most important topic, renormalization, but something that will be genuinely new to you will be the theory of abelian and non-abelian gauge theories. We're going to first build these field theories as classical field theories, then we'll deduce quantizations. This is where the path integral really comes into its own. So it's worth stressing that we don't really have a way to work with gauge theories outside of path integrals. That's changed, actually. I mean, we can work with canonical quantization now, much more difficult, or we can work on the lattice, which is something I hope to discuss in this course. So this part will be classical, and then we're going to talk about the quantization of non-abelian gauge theories. And there we have many options and many open problems. So I'm going to spend time describing how to do the quantization of non-abelian gauge theories using path integrals, which will probably be unsatisfying to a lot of you. And then we'll discuss how to do the quantization of non-abelian gauge theories on the lattice. This should be a lot more satisfying. And this is in fact how we do calculations at the moment for non-perturbative stuff. And then our last topic will be spontaneous symmetry breaking. And I really will only, I believe, have time to discuss the classical side. The quantum side, yeah, is more intricate. So that's the topics for this course and that general structure. There will be an exercise class every fourth lecture will be an exercise class. So that means Thursday next week is the first exercise class. The assignments will be uploaded about 7 days before. So you have 7 days to attempt the assignment. The assignment will be due on the exercise class Thursday next week. And you should also contact the tutor if you have any questions. All right, are there any other questions? Are there any questions to the structure or outline of the course? All right, let's get to it. typically people talk about path integral quantization. For the first part of this course, we're not even going to talk about quantization. We're going to assume we already have a quantum system. So the quantization is done. Where we begin. We suppose we have some known quantum system with a known Hilbert space and a specified Hamiltonian H hat. And let's suppose we've got, like, we're tremendously more powerful. Let's suppose we can even integrate the Schrödinger equation to get the propagator. So we've solved everything. We now know everything about this quantum system. The objective now is to get a representation for this propagator in terms of more classical data. That's what the first part of this lecture is going to be concerned with. It's all very well to assume you can solve the Schrödinger equation, but of course we're going to very quickly reach a situation where we cannot solve the Schrödinger equation, and every trick we have to help us along the way to solving the Schrödinger equation is a useful thing to know. And here's a really interesting trick for approximating this propagator here. So the first thing I want to point out is the very simple statement that if you take an exponential, then you can take its mth root and then raise it to the mth power. So that's a very useful observation. And you can let m tend to infinity. This is something that comes in handy and then you can expand this in a Taylor series, and then you actually have this identity, right? This is an identity for the exponential function. And it's this observation that we're going to exploit to get an alternative representation to our propagator u of t. So what's the idea? Well, I don't know how to work out the propagator. I don't know how to integrate Schrödinger's equation, but I probably know how to get from time t equals 0 to time t equals epsilon. That shouldn't be too hard. I mean, I know the Hamiltonian, I know t, and so this operator here inside the brackets, and I know the identity, should be pretty easy to apply. So remember, just think of this as a matrix raised to the power m. So let's call this matrix X. So inside the bracket we've got a matrix. The matrix is basically the identity matrix, and it's raised to the power m. And so the idea, which is no different from how you integrate a differential equation, is that you start somewhere, you evolve forward in time a little bit, and then that's easy to do, and then you do it again and again and again and again. So that's step one of the path integral. Step two is kind of more interesting. So let n be a basis for h. So I'm not going to say very much about what h is. Is it infinite dimensional? Is it finite dimensional? To make everything work here, we should assume it's finite dimensional, just so that everything converges and so on. But of course, with path integrals, we're very rapidly going to reach a situation where we can't talk about them as integrals anyway. But for now, we just have a basis for h. I'm going to be very unclear about what that basis is. Actually, I'll just call it j, just to be consistent later with my notation. So if we want to work out the transition amplitude to go from some initial state to some final state, we prepare our system in the initial state phi init, and we want to know what's the probability amplitude to get to phi final. Then the way to do that is to just apply the unitary corresponding to the propagator to phi init, which is this, and then work out that inner product there. And then if you want to know the probability that you made this transition, you just square that amplitude. So far, so nothing. And so now we're going to use equation star, which is this one here, to write this in terms of slightly more familiar objects. So far, so nothing. I just inserted one equation into another. Well, here comes the interesting step. We're going to insert between each exponential here the identity, which doesn't sound very interesting at all, but it's a very interesting identity. That identity gets put between these two exponentials here. We have another completeness relation here. And we do that all along this product of m terms. Super, right? That's you could do that. So once you've done that, you start to get something rather interesting. So if you look at this next expression down here, we see that the Hamiltonian appears, no exponentials anymore, the identity and the Hamiltonian like that. So what I'm going to do is collect together all those sums out the front and write that transition amplitude now as a sum of, well, we'll call them what they are, paths. Is a sum of paths, of classical paths, although I use the word classical relatively loosely, a sequence of paths of basis states. Now, if you look at this, this is a very interesting thing indeed. So this is some function of this path, what I'm calling a path, it's a sum over what I'm calling paths of some function applied to a path. So the picture I want you to keep in mind is this one here. Oops. So on the x-axis, I want to draw a picture with time running from 0 to t. So this is in particular, this is the time t over m, this point here, and that's 0. And on the y-axis is, I'm going to plot the basis state that the system found itself in at time whatever, jt over m. And the picture you should have in mind something like this. So we have a sequence of j values. Each of these j's is a basis vector. And we know, and we're going to associate with time it the basis vector j1. So that's going to be some, we're going to assume that the j's are in natural numbers for the moment. So maybe it's here, right? So at time t over m, I'm going to put a dot corresponding to the value of j1. Then at time t over 2, 2t over m, I'm going to put a dot corresponding to whatever value of j finds itself in this sum here. And so on. So, yep. Blah, 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 right? So this is a way to keep track of or to list the basis vectors that occur in this summation over here. So a path is a sequence or a tuple of m-1 natural numbers. And we're going to visualize such a path on a picture like this. And people might typically draw something like this, right? They might be tempted to connect these dots. This is a visualization of a path. And this identity that I've written out at the bottom of that board there tells us that the transition amplitude to go from the initial state to the final state is equal to the sum over all paths, which are none other than tuples of natural numbers, some function of these natural numbers. All I've done is write that thing out there in a different notation. Now this identity by itself is not very illuminating. The reason we like it is that it allows us to employ a sequence of tricks and simplifications that in many useful cases, in many interesting cases, allow us to calculate stuff. So if this was by itself all I was going to tell you, it would be very boring. But the interesting stuff begins now, which is, what is this function of the path? Well, obviously, to work out the function of the path, we need only know this data here. And once we have that, then we can work out the function of the path. It's just a product of these things for given j values and k values. And the way to proceed, the way that really leads to something interesting in the path integral setting is to write that as the exponential of some function L, j, comma, k. Actually, I suppose I'll just take out this I t over m. Yeah. Let me think. No, that was correct, sorry. Now we're going to identify this L in a moment. This is going to correspond to something called the Lagrangian, which is really the interesting observation here. Now notice what I've done here. So this is, you've got to be a bit careful in interpreting what I've just written. This here is, on the left-hand side here, this is a number, right? It's a number that depends on j and k, but it's a number. It's not don't think of now this as a matrix. That's the wrong way to think. Think of this as a number depending on j and k. And this number, well, you can always write any number as the exponential of some other number. That's all we've done here. This L is not the matrix logarithm of that matrix. That would be the wrong way to interpret this expression. This is a set of numbers defined by this equation here. And once you do this identification here, you get a very interesting formula indeed, one that was very suggestive when it was originally written down. Namely, you get an expression that looks like this. So you get a sum over all paths of the exponential of some function that depends on the path, and that function is this Lagrangian, as we'll see in a more concrete example. I should spend some words on, so that's the full, this is as far as you can get on the path integral without assuming something more about your system. So I should say some words on why the path integral is an interesting thing before we get to an actual more serious example. So there's several points that I'm going to mention here. So something that was extremely attractive when the path integral was developed was this realization that the path integral allows you to calculate quantum quantities in terms of solutions to a classical dynamical system. So this may not be as powerful a statement today as it used to be, because we understand quantum mechanics much better. But it allows us to take all of our expertise in solving classical systems and then use it to gain, as a calculational tool, to approximate some quantum transition amplitude. So that's a very useful thing, right? If you know how to solve one thing, then you may as well try and use it to solve another. And this is, oh, by the way, this way of using classical solutions to calculate quantum quantities works via this saddle point approximation to highly oscillatory integrals. So we're probably not going to see that in this course. We won't even need it, I think. The second thing that's so amazing about the path integral and why it will persist and why it's still useful very much to the current time is that it allows you to build completely different approximation schemes for this transition amplitude here. And the key word here is Monte Carlo. This is still the only way we know how to calculate non-perturbative results about the standard model or quantum chromodynamics. The way we do it is we are faced with this task of summing over paths the exponential of some strange function, which will turn out to be the Lagrangian in a couple of minutes. How would we approximate that thing? Well, you could use perturbation theory, blah, blah, blah. But the naivest thing you could think is, well, perhaps if I just sample over random values of these paths and sum up and build an estimator and just sum up this quantity a couple of times, perhaps this sum of random values will start to converge to the actual value that we get when we sum over all the paths. And although it doesn't work in the setting that I've just described, it does work in the setting of so-called Wick-rotated quantum field theory. And in fact, it's the only method we have, I think, to gain general non-perturbative results about interacting quantum field theories. So the trick is very simple. Right at your Lagrangian, start sampling over paths and sum up your estimator. The variance will start to go down as you sum over more and more paths, and you become more and more convinced that the number you get corresponds to the actual result of the path integral. So it's ever present in physics from condensed matter theory all the way to fundamental particle physics, the path integral. But at its heart, all it is taking a product of matrices and sticking in a complete basis between each matrix. We're going to now do this in much more detail for a specific example, namely a non-relativistic quantum mechanical system. Okay, I didn't really specify very much in this overview of the path integral construction. I said there's a Hilbert space and there's a Hamiltonian, that's it. So given a quantization, you can certainly write the propagator as a sum over paths of some scalar quantity that depends on the path. That's pretty much clear. Now what we want to do is assume a little bit more about our quantum system. We're going to assume that it has a Hamiltonian that comes from some classical, is inspired by some classical Hamiltonian. So we're going to assume we have some classical system in mind with a Hamiltonian h depending on the canonical position and momenta coordinates, and that there's more than one of these coordinates. We're going to turn around this derivation here to guess a quantum system corresponding to this classical Hamiltonian here. So if you look at this expression here, you can see the path integral tells us that the propagator is equal to a sum over paths of some quantity that depends on, well, the Hamiltonian. And these paths, if you restrict that basis to be a classical basis, like the position eigenbasis, it'll turn out that you can work out these transition amplitudes. So we're going to see that in some detail in a second. So the prescription is the transition amplitude for our potential quantum system should be given by a transition amplitude. Okay, it's not very deep. So we're going to turn the logic around. We're going to start with the classical Hamiltonian and try and find a quantum Hamiltonian that corresponds in some natural way to that classical Hamiltonian, and then via this path integral. So we're going to proceed as firstly as before. And we're going to insert the completeness relation between each of the products of E. So we first write E as a product of smaller exponentials, then we insert these completeness relations between each exponential. And because we're now working with a system with some continuous degrees of freedom, well, we have to use a slightly different completeness relation, but the idea is exactly the same as what I wrote before. That's the completeness relation in this case. We have a basis. The basis is the position eigenbasis, this improper basis that's not really a basis at all, but you're now, by now used to working with. And we're going to insert the completeness relation between products of little exponentials. So at the moment, the question doesn't seem particularly well posed. I mean, you have a classical Hamiltonian, and then I've written out this propagator in terms of some putative quantum Hamiltonian here. The relationship between these two things is not at all clear, but as we go through the path integral derivation in this example, you'll start to see how exactly this data appears in the path integral expression for this propagator here. So, well, typically, right, I've been using, I didn't advertise it, but of course, I'm going to write Q with a line under it to mean that it's the vector of canonical position coordinates. Likewise for the momentum. So we're inserting this completeness relation between all these exponentials, and we get this expression now for the propagator as a sum of lots of terms. We'll call this Jm minus 1. Ah, no we won't. Just as before, I've just renamed this basis from J to Q. And what we need to understand is precisely this term here, which we'll call star star in our example. What is star star? Yeah. So, yo. Oh, is there a minus missing? There absolutely is. Thank you. Good. All right, we need to understand this star-star expression in our example. So to make life easier, we're going to define Q naught equals QA and Qn equals QB. And to make life even easier, we're going to assume that our quantum Hamiltonian is some function of the quantum position operator. We're going to actually change this assumption presently. But suppose for now, to get further in this derivation, that H just happens to consist of some function of the position operators, or position operators. Well then, it turns out that we can do this calculation of e to the minus I h epsilon pretty easily in this case, because Q is the energy eigenbasis for a Hamiltonian of the form of f of Q hat. Couldn't get simpler, right? And it's this expression here that I think should most clearly highlight the connection between quantum quantities and classical quantities. This is some operator. This is some function of a classical number q of k. So we're relating classical quantities and quantum quantities in this step here. Now there's a couple of tricks that we're going to use to introduce momentum quantities into this story. So if we only had a way to express propagators for Hamiltonians that were functions of the position operator, that would be super boring because we know exactly how to diagonalize those Hamiltonians. We already have the eigenbasis. Now we want to get momentum into the story, and the way we're going to do that is use a different a complete set of basis vectors, namely the momenta. But before we do that, I'm going to note an identity. So before we get to this, dealing with the problem of the momentum type operators, I'm going to note a very simple identity about the Dirac delta function. If you do this infinite integral here, then you get the Dirac delta function. You can check that. It's an integral representation for the distribution. So we've got this expression for this transition amplitude here to go from time t to times t plus epsilon. And it's written in terms of this classical quantity f of q, but there's a delta function here. Okay, that's fine. You could just leave the delta function in there and just work with that. That would be perfectly okay. But we're going to see ahead that we're going to want to have Hamiltonians that are functions of functions of q and p. And with that knowledge, we're going to make this well-advised choice of a representation for the Dirac delta function and put that into this transition amplitude. So using that, we get a not very nice expression, but one that will be very useful. All right, so that's a take some looking at until you can see where it comes from. So this transition amplitude here that we were looking at Oh goodness. There's an I missing. Actually, yeah, this was nonsense, this term here. That it only makes sense when there's an f of q in there. So once you know how to calculate this, you of course know how to calculate the transition amplitude because you have an extra identity term. So that expression, once you use this integral representation for the delta function, equals this not very lovely expression here. Okay, we're going to note this for future reference. Let's call this I. So that's if the Hamiltonian was just purely a function of the position operator, this would be a way to express the path integral. You just take the product of all these terms and sum over all the values of q. So just note that this peculiar looking f of q plus k plus 1 plus q of k, because this is the delta function here that forces q of k to equal q of k plus 1, that's actually equal to just f of q of k. Yep, question? Is there a j missing at the last q? Yes, there is a j missing at the last q. Thank you. So you can do it. You can write that transition amplitude out like that. Now, why are we doing that? Because we also know that at some point our Hamiltonian is going to depend on momentum, and this momentum representation will be very handy then. However, let's now suppose that our Hamiltonian was instead a function of the momentum operator, which it usually is. Then we would need to calculate q of k plus 1 the matrix element of g of p hat. Now, that's not obvious how we would do that, right? Because how does the momentum operator act on a position? Yo, a question?
Sorry, but which q and which p is now a vector?
Which q and which p is now a vector?
You suppose that the Hamiltonian is a from vector q?
Yeah, so when there's a superscript, that means, and when there's an underline, it means the vector. So I should have put underlines here. And here, this is a vector inner product between q of k plus 1, which is a vector, or the jth element of q of k plus 1. All right, so here we've got the position eigenbasis, and here we have an operator which is a momentum operator. How does the momentum operator on the position operate on the position eigenbasis? Well, usually it's a derivative, yeah? So, yeah, you can put in, if you like, p equals minus I h bar grad, if that's something that you want to do. However, there's another way we could calculate this quantity here. We could do so by inserting a completeness relation, another one, but this time a completeness relation of the momentum eigenbasis. And then we're in a good state because g of p hat acts on a momentum eigenbasis element and it gives you a number. So that's super easy. And when we insert a complete set of momentum eigenstates into such an expression here, we encounter that inner product here between a momentum and a position eigenstate. So that is a Fourier phase, right? And we can use the fact that we know what that expression is to rewrite this expression slightly. And we get this really interesting expression up here. So remember that there is equal to pk, pjk, qjk. All right, good. We've calculated two examples when the Hamiltonian is a function just of the position operator or the momentum operator. But that's never the situation we find ourselves in interesting systems. The situation we find ourselves in usually is that the Hamiltonian is a combination of both. What if the Hamiltonian is a sum of some position operators and some momentum operators? This is the general case in non-relativistic quantum mechanics. What are we going to do then? Well, we're already done. Because e to the I epsilon h hat is the identity plus, or minus, let's say, minus I epsilon h So observing that the exponential of a Hamiltonian comprised of just two terms like this, that to first order it depends linearly on these operators like that, allows us to use both of these formulae inside in our transition amplitudes. So then we obtain, for the transition amplitude, using these two formulae that we've already derived, the following expression. So using these two independent expressions here for the matrix elements of an operator diagonal in the momentum basis and for the matrix elements of an operator diagonal in the position basis, we can exploit that to write the matrix elements of this transition amplitude here as an integral over momentum coordinates of this exponential quantity multiplied by that one there. So still, this is not an expression that produces vibrations. However, there's one more step that will make this much more interesting.
One question.
Yo.
Having the minus again. I think, I'm not sure, but I think in this expression, the minus on the first exponential is wrong.
The question is the minus on this first exponential, this exponential here, this exponential, is this minus sign wrong? Probably. Let's have a look. Okay, firstly I check my notes to see if I transcribed it onto the board incorrectly. Well, I have the minus sign there.
Because I think it comes from this delta function, and you change the minus sign in expression 1 by changing the qk plus 1 and the qk.
So the minus sign in expression 1. Up here you mean?
No, in
Over here?
this expression. Yeah, you don't have the minus sign in the exponential.
There's no minus sign here, that's correct?
That's correct.
Yeah.
Because you changed the
Yeah.
order of the qk and qk plus 1. So I think it's the same in
So, but this part here does not correspond to that exponential. No. It corresponds to this f part.
Yeah.
So there's a line I skipped. What I'll do is I'll raise the board, not that board, and then I will put in the skipped line. See that term here, this already corresponds to this pit here. Yeah. And so it's this, how about you, a quick way to answer this question is just in your mind, Taylor expand this to linear order. So then you get 1 minus I epsilon f of q. And that f of q is precisely that guy there.
Okay. Thank you.
Okay. Okay, so let's put it all together. So we're going to take this little transition amplitude that we wrote out here and multiply it n times for each of the terms in our original product of exponentials. And we get this super long, tedious expression. So that's the result. Yeah, it's not a very attractive expression. Yeah, question?
There are some hats missing.
There are no hats missing. These are all classical quantities now.
Okay.
That's the beauty of this expression. So this, in fact, in particular here, there's no hat, right, over the h. And yeah, I should have emphasized that fact, actually. That was probably the most important thing in the whole derivation, and I missed emphasizing it. We've taken our quantum Hamiltonian, which we don't know, and expressed this transition amplitude in terms of this classical Hamiltonian. Now, usually, I've been telling you, you should always be very, very careful, and it's super stupid to just put hats on things, because the relationship between these two is a complete category error to say that the classical Hamiltonian is the same as the quantum Hamiltonian. But this derivation here makes clear that there's a very quantitative and precise connection between these two things in certain special cases. I'll mention those in a minute. So yeah, very crucially, there's no hat in that expression there. Now, you may think this is an ugly expression, but actually this is the expression we use up to a factor of I when we do Monte Carlo sampling of quantum fields. There's no way to make this more beautiful and elegant. It's just what it is. Now, to a large extent, this can be made rigorous. So everything, you may have heard that the path integral is not a rigorous thing. Well, indeed, the next expression I'm about to write down will explode any hopes of rigor. But this one here, this is good. This is actually this expression works. You can make sense of this if you work very hard in functional analysis. And it's a useful representation for the propagator. Why is it useful? It's useful for multiple reasons. I'm resisting writing down the next expression. The next expression is so elegant that it's misleading. This is it. This is with all the dirty, horrible details, all the warts. This is what the path integral really is. And it's already remarkable. It's remarkable for many reasons. So remarkable reason number one, there's no hat here, right? So you could there's no hat on the right-hand side. So you can use it to define a quantum system. So you could use the right-hand side as a definition of a hat, of a hatted version. So it's a scheme to guess quantizations. It doesn't always work. In fact, it basically only works when you know the answer. But hey, it has actually, for fields, it's much more useful for guessing hats. So that's like sort of extremely remarkable point number one. It's a scheme for guessing H hats. Because all you need is the classical data, pop it in, and you're done. You have the right-hand side as some expression. Secondly, via saddle point methods, it gives an approximation scheme for this transition amplitude. So why do I mention them with saddle point? Well, look at this. Well, we've got this highly oscillatory bit here. We've got an integral of an oscillating exponential multiplied by something else. No, in fact, that's it, right? The basic transition amplitude is just a highly oscillatory integral like this. And in complex analysis, you've learned, I assume, that you can approximate these highly oscillatory integrals in terms of the saddle points, the critical points of this exponential function here. And those critical points, yeah, I guess I will mention it later in the course, correspond to classical paths, classical solutions to the classical equations of motion. Pretty remarkable. And that can be made pretty rigorous indeed. It comes under the name of various theorems, Duistermark-Heckmann theorem, for example. And three, saddle point, Monte Carlo. build an estimator for the right-hand side, sample over classical configurations, sum up your estimator, have an approximation to the transition amplitude. 3 fantastic reasons to love that expression as ugly as it is. But now, I want to write down an expression that's crying out to be written down, but which leads you down a path of woe and misery if you take it carefully, take it literally. Take a look at the right-hand side in the exponent. You see an epsilon up there, and you see a sum over k. Whenever you see an epsilon and a sum, you should be thinking about integrals. So tempting, isn't it? So in the limit that n tends to infinity, the number of points where we inserted the completeness relation, in that limit, the exponent becomes extremely nice indeed. That thing in there, this horrible expression up there, is the discretized form of a very interesting exponent, a very interesting function, namely this one. Right? Just look at that exponent there. Just, if you don't believe me, just expand, discretize time again, and replace the integrals with epsilon sums. You see this q dot here, that q dot here cancels the missing epsilon up there. So I hope that's not too controversial. I mean, that looks... Is this problematic? No, no, this is perfectly rigorous. This is nice. Nothing wrong with that. But what on earth do I put in here? So I've taken a finite number of integrals, and I've taken a limit of those number of integrals goes to infinity. I have to put something there, right? The integrals haven't vanished. Well, what we're going to do is we're going to simply just define the limit of the infinite number of integrals. We're going to give it a symbol. And that's the symbol we're going to associate to those infinite integrals that you get when you take n to infinity. And then we're going to, yeah, and then the fun begins. So this is, what is this thing? I mean, it's very clear what that thing up there is. It's just a bunch of integrals. But when you have an infinite number of integrals, what is that thing? So I'm going to have a little... I got 5 minutes to philosophize on that expression there a bit. If you take this literally as an integral, you are in for trouble. So in the strictest mathematical sense, this is not an integral over any measure space.
Well, there is a Wiener measure.
Ah, yeah, you're jumping ahead. I was going to get to this. So in the case where you have not an oscillatory integral here, but a integral which was real and didn't have an imaginary component there, then you can make sense of this thing here. It's called the Wiener measure, or it's a measure on Brownian motions. But that only works when there's no imaginary term in the exponent. So yeah, there is, it's sort of extremely hard work by many mathematicians over the past 50 years have made sense of this in the case where there's no I. I would love to talk about that. I could talk about Brownian motions for 2 courses, but we're not going to do that because we're not going to do any quantum field theory then. Instead, oh yeah, and if there is an I, then as far as we know, this is not an integral in any sense over a function space, a measure space. It's just nothing you can do about it. that the interpretation is so tempting. It's a sum over all paths, like these Q's and P's. If you plot them in the sense that I did right at the beginning of the lecture, you know, you've got time, you've got time t here, and you've put in an infinite number of subdivisions. And then these values of q at each time, you can think of them as a dot on this picture like this. And it's very tempting to join up those dots. And say that this is really an integral over paths. So this is q, this is time. You sum over all possible paths. I mean, I even wrote it at the beginning of the lecture, right? But as soon as you say path, then you're really in trouble, because these integrals at the top, they run from, you know, q equals minus infinity to infinity at time step k, q equals minus infinity to infinity at time step k plus 1, and so on. So these paths are highly oscillatory. They're jumping around all the time. In fact, they're almost always never continuous. So this picture that people draw of like, as though there's a classical trajectory running through the system is sort of maximally wrong in interpreting this expression here. Nonetheless, it turns out with this saddle point approximation to be absolutely correct. So the paths that you sum over here, you can take to be continuous and near the solutions of the classical theory. So you have two options before you. One is you work with this expression as though it's a nice integral, admittedly over a big space, and just do all the things you would normally do with integrals, but then admit that it's not rigorous. Or option two, which I actually recommend given what I'm going to say about effective field theories later on in the course, is this. This is just a representation, a symbol, if you like, for that more ugly object up the top, which makes perfect sense. So whenever you see this written down, and I'm going to write it down a lot in this course, you go, oh no, this is not actually what's meant. What's meant is that there is some n, some finite lattice somewhere, and we really replace this thing always with that thing up above. So this is just like a box that produces lots of integrals. So that's the option that I'd like to emphasize in this course, because that actually fits very nicely with what I'm going to tell you about with renormalization theory. At some point, we're always going to put a cutoff on our theory. We're always going to put our theory on a lattice, be it position or momentum space. And the minute you do that, you replace a horrible thing, well, a beautiful thing like this, with something that's horrible / beautiful like that, but which makes complete sense. So I think that's actually a good moment to stop. In the next lecture, we're going to calculate, for one key example, this path integral here. And then we're going to apply it to classical fields to build quantum fields. So that's the very good payoff of all of this, is you get quantum fields extremely quickly from the path integral formulas. But for now, I think we will stop. Thank you very much.